Yes? It was what? What did you say it was? It tells you where, so in that particular one, what one is that? Number 3, is it? Sine of theta is minus root 3 over 2. So you're talking here and here. So it's definitely bigger than 180. They are the two places. Yeah, go on. Yeah. Well, if it's not positive in those two, it must be negative. So they're all positive here, sine is positive here. So then sine must be negative in the other two places. It's either positive or negative. So we identified the two positive places, and then by exclusion, therefore we identified the two negative places. So that's these two. That's why I picked on those two. And I know root 3 over 2 is 60 degrees and 60 degrees. So it is 240 and 300. They are correct. Are you sure of that now, Rory? Definitely, because you don't want to get caught on those. The next one was 135 and 225, and the one after that, part 5. Well, sure, you can look up the answers. So why am I calling these out to you? They're in the back of the book. 60 degrees and 120 degrees. So you'll know whether you had those or not. You'll check the back of the book, and you'll know why. So anything else on homework? We'll go direct now for the rest because class has started. So anything else on any of the rest of the homework? Yes, go. Question 4, part 2. The sine of theta is 5 over 13. So the sine of theta is 5 over 13. And what am I looking for? I'm told what else? I'm told theta is obtuse. So I know the two places that it could possibly be is there and there, right? But because it's obtuse, it can't be this one. Right? So all I have to do now, I now know in this section here, cosine is negative, and I know tan is negative. So at least I've identified the SIG ends of those two. Now it's a matter of figuring out a little triangle here. This is 5, this is 13, so this piece must be 12. Yeah, using 5, 12, 13. We met those numbers before, didn't we? So therefore I know the cosine of the angle then is 12 over 13, the adjacent, but it's a minus, and the tan of theta is 5 over 12, and that's also a minus. And that's it. Did you get that? Oh no, yeah, don't worry about that. We're only dealing with the triangles. This is a ratio of 5 and 13. So this is actually what we're talking about then, really. That little triangle there is really what we're talking about. No, that's okay. Anything else, anybody? Question 5. The cos theta is equal to cos theta over 2 is equal to minus root 3 over 2. Okay, so we have the cos of theta over 2 is equal to minus root 3 over 2. So again, from a picture point of view, Rory, tell me where here. First quadrant, second quadrant, third or fourth. So where are we talking about? Second and third. Good man. Okay. So therefore, we now have the cos of theta over 2 is equal to, I've written that already. So I put in my dot for my angles. So I'm going to now do my reference angle is the inverse cos of root 3 over 2, which is 30 degrees, I think, isn't it? Hopefully you're getting 30. 30 and 30. How's that? So we're now saying it is theta over 2 is what were we looking for? Angles between 0 and 360, is it? So we're okay with this. So theta over 2 is equal to 150, or theta over 2 is equal to 210. Would that be it? Theta over 2 is 150. Theta over 2 is equal to 110. Now, or 210. Now, I could go and write out the general formula. Generally, I do write out the general formula when it isn't just theta or when it isn't just x. But because it's theta over 2, that isn't even a full theta. So I know I don't have to. No, I wouldn't go wrong if I did. So if that's what theta over 2 is, then theta is equal to 300. And theta is equal to 420, and because we're told it must be between 0 and 360, we only have one answer in that case, 300. Now, you know, normally when there's a number, when it isn't just cos theta or cos x, we normally do the general, like if it was cos 2x or cos 3x, which is what the bulk of question 5 is about. But because it was theta over 2, really what I'm saying is I only need to use half a circle. That's why there's only one side to it. You know, that's why there really is only the first. So I know that I don't need the second half of the circle at all. But it's as easy. Either way, it doesn't make a difference. How many of you got that? Only a few of you. How many of you got as far as the 150 and the 210? And didn't get it out and didn't finish it? Who didn't know what to do there now? Okay, why didn't you know what to do? I'm just wondering why didn't you just work away as normal? And then at the end decide, right, it was theta over 2 I'm dealing with. Just work away as normal, and when you get to the theta over 2, 2 theta wouldn't have presented you with... Did you do the N360 with that now? Did you do the N360 with that? No. But why is that any different, say cos theta over 2? Why is that any different to cos 2 theta? But did you get out the cos 2 theta one? Part 2? Yeah, it's identical, it's just... Except that you only have half the answer, you just follow the thing with it. We'll actually be meeting one very similar to that now in a while. Anything else, anybody? Now, did everybody in the room get the most of those last night? Everybody in the room. Because you cannot face your Leaving Cert without being able to do those. Is everybody happy with those solving? We'll be meeting more. We'll be doing these until June, but you've got to get to the stage where you don't even blink an eyelid when you see one of those. You just continue the same as if I asked you 4x equals 8, what's x? You don't even think about it anymore. There's just one or two little odd ones in the middle of all that, and I was thinking of this actually coming in the car this morning. So you have nothing else to be doing. I was listening to the news, but something like this: the sine of x is equal to -1. Now, for the ones and zeros, you should not need a calculator. You should never go near a calculator for the zeros and ones, because you know the answer from the unit circle in your head. There actually, in that case, is only one answer. And that's 0, 1. And this is 0, -1. For the ones and for the ones only, there is only one answer to this. And you can read it off there. X is equal to 270 degrees. So it's an easy one, but people are expecting, where the hell is the second answer? Because you told me there was always two answers. There isn't always two answers. There is only one answer for the ones. There's only one, technically for the sine of 0 and the sine of 360, it's kind of part of the same circle. But like, look at that. Sorry, the cosine of 360 or the cosine of 0. The sine of 90 is 1. But the sine of nothing else is 1. The cosine of 180 is -1. The cosine of no other angle is -1. But for all the other angles, you know, there's two possible answers. You know, the sine of x is a half. There are two answers here and here. But for ones and -1s, there's only one answer. And you kind of need the unit circle. You don't really need your calculator. Well, you can, your calculator will give it to you. But just be aware of that. I'm just pointing that out to you now. Like there was one there, it was the last one there. The sine of 3 theta is equal to -1. This is question 6, part 5. The sine of 3 theta. I love to see the ones and the -1s because I'm doing a unit circle in my head. When I see the ones, or the ones and zeros, like I'd love to see this question. The cos of x is equal to 0. Because off the top of my head, I'll do my unit circle. 1, 0, 0, 1, -1, 0, 0, -1. So I know straight away here, x is 90, x is 270. So the ones that are equal to 0 are lovely, easy ones to do. But they catch you in an exam. They actually, because you're hitting buttons on a calculator and you can't find a second answer. So for the ones and zeros, it's in front of you, the unit circle in your head. So that one there, the sine of 3 theta is equal to -1. I know there's my answer. So that's what I was saying. So that is, it's question 6 in your book. Question 6, part 5. It's the last one there. Question 6, part 5. There is actually only the one. I'm only doing, I mean, there's a general answer to this, obviously. But from the first circle, you'd just simply be saying 3 theta is equal to, what was I saying, -1. 3 theta is equal to 180. So theta is equal to 60 degrees. Whatever you'd be saying with that. No, sorry, 270, 270. This one here, this one. The cos and the sine. Remember, the sine, I was looking at that. It's this I'm looking at. The sine is -1, so theta is equal to 1/3 of that, which is 90. Now, in that particular question, they're looking for all the answers. So I'll just redo that one again now because I got distracted with the other one there. The sine of 3 theta is equal to -1. The ones and the -1s I do in my head, I do off the unit circle. Now, you probably need a bit of practice on those unit circles. Don't forget, do this thing, do exactly like I'm doing. 0, 1, that's cos sine, -1, 0, cos sine, and 0, -1, cos sine. So therefore, I would be saying that 3 theta is equal to 270 degrees plus n times 360 because of the 3. Because of that 3, I'm doing the general answer. So then theta is equal to 90 plus n times 120. So that's the general answer to that question. So just all I'm pointing out to you is for where the equation is equal to 0 or where the equation is equal to 1 or -1, then work off the unit circle. Don't be bothered with a triangle or a calculator. Go and do something like that. So it's from the diagram that I come up with the answer. Because the ones and the -1s, there is only one answer. And you'll see that later on when we do graphs, trigonometric graphs, you'll see there is only one answer. But for now, we're having a look at that. Is that okay? So just be aware of that. That's something now, I've said it once, so just you have to try and remember that, so maybe write it somewhere in your book or something. It's one that you trip up on, very easily trip up on it. Okay, just in light of this, and this is a nice easy one again, the sine of x is equal to 1/2. Sometimes we measure angles not in degrees, but in a thing called radians. And we're not going to get into this in detail just now, but I'll come back to it later on. What is a radian? A radian is a radius. So if this just happened, have a radius of 4, that circle, and if I came up and I measured this distance and let it equal to 4, so if I made the arc of a circle that I would draw, if I let it equal to the radius, then what I would have in there is 1 radian. So the angle there now is 1 radian, and you can think of it as 1 radius. The arc is after making 1 radian. So it's 1 radius. That seem okay? So if you make an arc equal to the radius, then the arc you've opened up happens to be 1 radian. So 1 radian, I should write there, 1 radian. And I'm just putting the word radius in so that you kind of see the link between the two of them. Now, we're not going to get into heavy detail on this just this morning, but just to be aware of that. So you tell me this. If this radius is 2 and I make an arc of length 8, what's the size of that angle? So if the radius is 2 and I make an arc of size 8 or length 8, what is the size of the angle in radians? Remember, if I make an arc exactly equal to the radius, then I have 1 radian. Obviously, if I make it 2 radiuses, it's 2 radians. So how many radiuses have I made? Many radiuses have I made? Well, Shout it out. A radius is 2. I've made an arc of 8. So how many radiuses is that? Hello? Contact the living, join hands. Well, 4. So that angle there is 4 radians because I've made 4 radiuses. So 4 radians. Here's a very simple formula. The size of the angle is the length of the arc divided by the radius. Look at that. Lovely, handy little formula. The angle in radians is the length of the arc divided by the radius. The length of the arc divided by the radius. So now you have no bother in working out the size of. So I'm going to ask you to do this one. You shouldn't need a calculator for this. So how many radians have I there on the one on the right? All you're asking is how many radiuses have I drawn there? So hopefully everybody is getting 5. Are you? Getting 5? So just keep that now and park that. We'll be coming back to that later on when we do areas and volumes. Because there's something I want to show you now. Supposing I draw a circle, and there's my radius. I'll call it R. Call it R. And this time the arc I draw is all the way around. So I've gone around the full circle. Now what's the length of that green line? What's the length of that green line? Anybody have a go at that? What's the length of the green line? Pardon? It's the circumference of a circle, which is 2 pi r from your junior cert, 2 pi r. So remember we said the angle is the length divided by the radius, so it's 2 pi r divided by r, so we're getting 2 pi. So what I'm now saying is that in a circle, there are 2 pi radians. And there is the link between everything. A full circle is 2 pi radians. So we have done that logically. I have made, now that pi, by the way, is our famous pi, 3.14, that's what it is, 6.28 radians or thereabouts. So it's the same old pi, 2 pi radians. Now, the whole establishment of this then is, I can say then that in 360 degrees is 2 pi in radians. So we can now measure an angle in radians, or we can measure it in degrees. We've been so used to doing it in degrees. Here is a great link. 180 degrees is pi radians. 90 degrees is pi over 2. 45 degrees is pi over 4. 60 is pi over 3. And 30 is pi over 6. They're the ones you kind of need to know. There are other ones, obviously. You can work out any of them. But they're the ones that you kind of keep in your head. That 45 degrees is pi over 4. 90 degrees is pi over 2. So half a circle is pi. Half a circle is pi. On page 13 of your tables, that grid, I think the top part of that grid is in degrees, and there's another line with it in radians. So just to find that link there now, there are 2 pi radians in a circle. 2 pi radians in a circle. We all right? Now, the grid in your tables looks something like this: 0, 45. Oh, geez, no. 0. Don't need to take this down because it's in your log tables. 45, 60, 90, 180. I'm not going to finish it. But underneath it, they have 0, pi over 6, pi over 4, pi over 3, pi over 2, pi. And along here then they have cosine, sine, and tan. And, but you can read off pi over 6, you can read off whatever the numbers are. That's in your tables if you have a look at it. Now, what's the big deal about this? The big deal is if I give you this, the sine of x is a half. Find x in radians. It's just a different version of it. Find x in radians. Now, if you go to your calculator and you change the function, I can't remember how to change these particular ones. It's a shift mode 4. It goes into radians. Now, if you type in now, so if you type in, well, first of all, we'll do this. Look, we'll do the same way as we normally did it. This is the same way as we normally do this. We know it's here and we know it's here. Does everybody understand, without me pointing out to you, why I draw those two lines? Do you all know why I'm drawing them where I am drawing them? This is our dot. This is our other dot. Okay, we now say x is a reference angle. I won't say x, it is x in this case, is the inverse sine of a half. Now, if you go to your calculator now, you will be told that it's pi over 6. So the calculator does that for you, pi over 6. So now I'm putting in pi over 6 in there, and I'm putting pi over 6 in here. So what are my real angles then? So x is equal to pi over 6 is one answer. Now it's a little bit more difficult to subtract, to find this angle here, well, there's one angle. To find the green angle, it's a little bit more difficult to find it. Now, your calculator should do this, but you shouldn't have to do this. So I know you can do it with a calculator, but you shouldn't have to. This is pi, and I want to subtract pi over 6 from pi. The best way of doing it is to say that pi, I want to write it is 6 pi over 6. That's what it is. It's a full pi, so it's 6 pi over 6. And I'm short 1. So this angle here must be 5 pi over 6, because I'm taking away 1 from it. So the full way, the halfway around will be 6 over 6. I want to take 1 over 6, so I'm left with 5 pi over 6. Now, your calculator will subtract that for you, but there's a bit of typing in to do that. You shouldn't have to do that on a leaving cert higher level. You shouldn't have to be going to a calculator to subtract. All I did was really got a common denominator, change that into 6 over 6. I know that this is 12 pi over 6. So in my head, I'm doing this 6 pi over 6, 12 pi over 6, whatever I need. And that's how we do it with radians. I'll do another one, and then I'll let you try one. Let's say we have the cos of x. Oh, geez. The cos of x is equal to, I'll go from minus a half this time. Again, I'm not even mentioning this anymore because I hope you have all of this yourselves. You see the bother I'm going to, putting in the dot. I'm being very safe about this, putting in the dot. And then the reference angle is the inverse cosine of a half. No minus being mentioned there. So that turns out to be, if you go to your calculator, it's pi over 3. That's pi over 3 there, and that's pi over 3 there. Now, looking at that, what are my real answers? Without going into the need of a calculator there now, what are my real answers there? Okay, remember this is a full pi, this bit. And in this case, it's in thirds I'm interested in writing it. So the full pi is 3 pi over 3. So to that black dot there is 3 pi over 3. So what are we looking for? We're 1 short of that. So we're getting 2 pi over 3. And also we're 1 beyond that, which is 4 pi over 3. So there's our 2 answers in that case. So this is, again, look, you'll just take it nice and slowly. No need to rush with this. There's my 3 pi over 3, that's pi. Then I'm 1 short and I'm 1 extra. That's 2 pi over 3 is 1 short, 4 pi over 3 is 1 beyond. Now, there's all sorts of ways of getting around that. I'd just like you to get comfort. You'll never get, because you don't meet it often enough in the Leaving Cert, you'll never get extremely comfortable with pies and stuff. Now, those doing the applied maths would, because you meet it quite a bit. But those who, you generally don't meet it that often. Now, we do meet it in complex numbers quite a bit. But it's nice to get reasonably comfortable with it. I'm a great believer in using fractions, like I'm writing that as 6 pi over 3. And, take your time with it. There's no need to panic. that's what you do. We're pi over 3 short, etc. So tonight I'm going to get you to do question number 2 again, but this time I want the answer in radians. Last night you did it in degrees. Tonight I want you to do all of question 2 in radians. And take your time with it now. Do you get, I'm going to give you one to do now in a second, just to make sure that you kind of know where you're going with this. So I give you that one to do. The tan of x, you can do that now, please. The tan of x is mine, and this is what they'll have written beside it, by the way. They'll have written 2 pi. This is page 240, question 2. So this is the one I want you to do now. Nice and slowly now. Something here. Right, I'll just go one more gear with that. What about if it was tan 3x is equal to minus, no geez, I'll do 2x, it's easier. 2x equals minus 1 over root 3. Again, you can see there's no solutions to it here, or there's no limits, ranges to it here. So we're back to the same crack again. I'll just draw the diagram so that if anybody's looking at this later on, they'll get an idea of what we're doing. Here and here. Eventually, we know the answer here. Pi over 6. Pi over 6. And we know the answer. I'm going to go with this now. So you know this from the previous one. 2x is equal to 5 pi over 6 plus 2n pi, and 2x is equal to 11 pi over 6 plus 2n pi. Now, it's very easy to do the next line. You divide across by 2. Same as we did normally. You write the general form first and then you divide. Remember that yesterday? The mistake you make is that you divide first. No, you don't. You don't divide first. Remember, that's the mistake you make. We do the general first and then we divide. The general first and then we divide. I'm now going to divide. I'm not, because I want to show you one other thing that I always do. For safety, I always do this. I always get a common denominator. Now, you don't have to, but I always get a common denominator on the right hand side here. Now, the quick way of doing the common denominator here, because it'll be the same thing you'll be doing the whole time, is you just multiply that 6 by the 2. So I'm going to get 5 pi plus 12n pi over 6. And over here, I'm going to get 2x is equal to 11 pi plus 12n pi over 6. And then my next line here would be this. Otherwise, you end up with funny looking numbers. So it's a little bit longer, as you can see. I've divided across by 2 there, and I get 12. So there was a next. Now you don't have to do that middle line. You could divide across by 2 there, but you're going to end up messing with adding pi over 3s and pi over 2s. You're going to adding various funny numbers. I prefer to get the common denominator on the right hand side. Now all I have to do, now we still have to go with this. I let n equals 0. So the answer is 5 pi over 12 and 11 pi over 12. And then I let n equal 1 and I get 17 pi over 12. And I get 23 pi over 12, which is nearly the full circle. 23 pi over 12. So I put in this thing here. I put that thing in the top in case you're taking that down now. I never put in the range of those. This is the answer if there was no range in there. But because there's a range in there, I just wrote it in now. There's my, you can see that last one is nearly the full circle. It's nearly 24 pi over 12. It's nearly 2 pi. That one there is nearly 2 pi, so you know you've nearly gone around the full circle. Look at that now. Like that, you can see how you deserve marks if you get that thing out without falling off the wheel somewhere. You can see that it's easy enough to get to here. You know, 2x equals 5 pi over 6 plus 2n pi. 2x equals 11 pi. Now you can try it by dividing x here first. Dividing 2 here first. But if you divide across by 2 here, you're going to get 5 pi over 12 plus pi. And then you're going to be adding a pi over 12 and a pi. I prefer to get the common denominator. It makes the addition later on much easier. So to get the common denominator, just put that 6 up there. And it becomes 6 times 2 is 12. And then it's easy enough to write the right-hand side then. And then divide across by the 2. Little bit of mess in there now. So that's what you will be doing tonight. Oh, geez, you won't. I better make you do one of those tonight because they're all x's. I'll tell you what I'm going to ask you to do. Can I get you to do question 2 again? Can I get you to do the top line as x's and the bottom line as 2 x's? So the top line is sine x, cos x, sine x, and the bottom line is tan 2x, sine 2x, cos 2x. Please. So do them like that. Now, please ask me about the one that's on the board. Is there anything there that will frighten you the day of an exam? You have to be very steady with that. It's so easy to go wrong there. The biggest mistake, I'm still saying it, the biggest mistake is where you put the red dot. That's what's going to cost you an awful lot of marks, some of you. The red dot. You should be able to get as far as the starry bit there handy enough. 5 pi over 6, 11 pi over 6, stick on the 2n pi. What do I do next? I think the safest thing to do is get a common denominator and then divide across by the 2. Because then there's no messing when you get to here. It's just adding ordinary numbers, you know, put n equal to 1 and just add 12 and 5, 17. Grand. There's no messing with it. Anybody want to ask me anything about that now? I think that's tricky enough. That kind of thing is tricky enough. Much prefer to work in degrees because it's so easy to work n360. It's no bother to do that. Anybody want to ask anything? Try again tonight anyway and see how you get on. All right. Was there something else I wanted to say about that? I don't think there was. Okay, I'm actually going to do another little pieces. I want to get away from all that solving stuff and that stuff that you're kind of familiar with. At junior cert, you worked with triangles. You worked with only right angle triangles. And you had all the routine. And I told you to do one of these, you need 3 bits of information. Apart from the 90 degrees, you need 3 bits of information to work a right angle triangle. Sorry, wrong word. You need 2 bits of information. It's the next one that I need 3 bits. You need 2 bits. Apart from the right 90 degrees. Now, if you include 90 degrees, then that is 3 bits. But apart from the 90, you just need 2 bits of information. Looking at that picture, I should be able to work out anything I need to know about that triangle once I see 2 pieces of information. If I want that side there, then I simply say the sine of 30 is x over 5. I know the top angle above by just looking at it. If I want the bottom bit there, I'm using cosine 30 is equal to x over 5. So I can fill the whole lot in any way I like. Or even if they just give me 2 pieces of information like there and there. So I can work out the missing side here, and then I can work out the opposite over the hypotenuse. I can work out that angle. So you can. That's junior cert stuff. 2 bits of information and you can fill any triangle. And I'm not going to delay on that. 2 bits of information. And I'll tell you why in a few minutes, why I don't. At Leaving Cert, we deal with non-right angle triangles. And there are only 2 formulas that we deal with non-right angle triangles. I'm going to show it to you. This is the way they label a triangle at Leaving Cert. This is a non-right angle triangle. If they call this angle A, then they call this side A, small letter. If they call this angle B, then they call that side B. And if they call this angle C, this is going to look funny because it's 2 C's. You don't know which one is big and which one is small. That's what they give. Now this used to be on the old junior cert course, this particular one, but they've dropped it now. They only do right angles for junior cert. There's a lovely, lovely formula to use to solve triangles when they're non-right angled. There are two formulas. One is called the sine rule and it has an E on it. It's called the sine rule. And this is the formula. A over sine A equals B over sine B equals C over sine C. That's called the sine rule. How many of you have this done before? A few of you. Okay, now sometimes you see that written the other way around. Sine A over A equals sine B over B equals sine C over C. In fact, you'll find me using that because in my head it's stuck in it like that. Sine A over A equals sine. I can't remember actually which way I use it both ways, but it's just one I instinctively go to. Now, in actual fact, you don't need that big long formula. It's in your log tables. The truth is, you only need two parts to it. Any two, doesn't matter which two. You only need that picture. So even though the formula is A over sine, and we have to prove this formula as part of your leaving cert, but we won't do it just now. A over sine A equals B over sine B equals C over sine C. I call this the crisscross rule. That's what I call it, the crisscross rule. And I'll show you, it's so simple to work this now. It's very straightforward. How you will know when this formula works. Okay, all right. Geez, sorry, no, some people were missing that there. There you go, I'll just leave that there. This would be a typical sort of question. If this is 30 degrees, and this is 8, and this is 60 degrees, what's this here? Now, why I call it the crisscross rule is because you do a crisscross inside the middle of the picture. And if your picture looks like that, where you have two things connected and two things not connected, then you can use this formula. Now, that's it. I know this formula works. In these non-right angled triangles, I need 3 bits of information in order to make the triangle work. I need 3 bits of information. But I always draw that picture and I always do a crisscross, because once I can do a crisscross, and as long as I'm connecting 2 pieces together, I know I can use this formula. So as long as I can do one line joining, and here's how I do it. It doesn't matter which one I call A and which one I call B, as long as I put, remember the A's are opposite each other, so as long as I put the opposites on top of each other. So in my example here, I would be writing this as A over the sine of 30 equals, I can call it B over the sine of 60. There's no real need to call them A's, B's and C's. Just one side over the opposite angle equals one side over the opposite angle, like that. So as long as you could do a crisscross, 8 over sine 30 equals X over sine 60. And basically you work out B then. So I'm going to get a straight line here first. So B times the sine of 30 is equal to 8 times, I haven't done no calculations here yet, so then B is equal to 8 times sine of 60 over sine of 30. And what is that, 4 root 3? I'd say 8 root 3 is the answer to that, but we can look it up and see. 8 sine 60, oh, I'm in radians, geez, there we go now again, see, there's a catch, careful. So 8 times the sine of 60 divided by the sine of 30. Yes, it was 8 root 3. I know, I needn't even look at it. It is. I better look at it just in case. 8 root 3. Yeah. Okay. See the little catch there now? I did it myself. Got into radians. I used sine. I put in sine 60. If you go back to radians and you type in sine 60, just so you'll know that you've done something wrong. So if I put in the sine of 60 and I'm in radians, I'm getting an answer of minus 0.304. I know I can't be getting a minus because the sine of 60 should be positive, so it can't be a minus. But it's very easy to make that mistake now. It really is. You've got to be wide awake for it. So it's a lovely, simple rule to use. You look for your 3 bits of information. If you can do a crisscross, and you say to yourself, when won't you be able to do a crisscross? If you had this. Now you see, I know I can't use the crisscross rule on that because I can't, while I have 3 bits of information, I can't connect two pieces of information together. So I know I have to use something different. And that's what the other rule is. For the scenario that this one doesn't work, then the other one will. So I'm going to just throw you in at the deep end here. So I'm going to make this 10. I'm going to make this 9. And I'm going to make this 40 degrees. So I want to know what's that angle there. I'll write the rule again for you so you can see it. I'm not even going to write the other bit. You don't need the other bit. Now, you should be getting to here. Are you getting to there with the question? The sine of x is 0.714. Are you getting that? Everybody getting that? Are you? Is that the right? Okay. Now, yesterday's work, we now have to do. We now have to do this. Unfortunately, now you can see how the question will extend. The sine of x is positive, so it could be here or it could be here. So if I do inverse sine then of 0.714, it's giving me 45.56. Now do you see how it becomes a big question? 45.56. So then x could be 45.56. Or x could be according to this 134.44. Now, could it be 134.44? Could it? Because the other angle is 40, that means the two angles come to 174.44. So there's still 6 degrees that the top one could be. So it is possible that there could be 2 answers to this. More often than not, you will get an answer here like 150. And you know it can't be because we've already got 40 and now we have 150. So it can't be 190 in the triangle. So more often than not, there will only be one answer to that. But sometimes it's called the ambiguous case. There could be 2 answers to it. There could be 2 ways you could draw that triangle and end up with, you see, I could, if you look at the picture, even the way I have it done, if that's 40 degrees below, you imagine me, I'm saying the other angle is 134, which means the top angle is about 6 degrees. If you imagine me with the 10, there's what it is right now. I could decide that I was going to draw that in like that and still be 9 in length. You know what I mean? I could make a triangle which looks like that picture there, or I could draw a triangle which looks like this picture here. With 10 there and 9 there, and a very small angle here. You know, or whatever way you'd be drawing it. That's the way we'd be drawing it. I could do that with it. Anyway, that's known as the ambiguous case. So, again, I'm going to give you one to do. Let's see. $76.2 degrees, 8, 45 0.4 degrees. What's this here? I'm getting an answer of 5.865. You getting that? Whoa, what did I do there? Jesus, what did I do there? Oh, I hit the wrong button, hit the home button. There we are. How are you on that? That working out for everybody? You sure? So you can see it's a lovely question. Should it come up in the exam? It will come up probably in a separate question to the ones we've been doing for the last bit. As well as that question 2 that I'm giving you tonight, there's a one on, it's 2018, it's this is paper 2, question 4 part A. 4 part A of 2018. And I think there's another one, I think it's 2016. Now, the more you practice at these, the better you're going to get at them. Yes, it's 2016, question 3, part B. Question 3, part B. Oh no, sorry, Jesus, cancel that. You can't do that. You can't do it. Sorry, cancel that. I also want you to do, this is on page 244, just do a couple of these triangles. I want you to do question 1, 2, 3, 4, and 5, but I only want you to do the first part in each one. So the first part in question 1, first part in question 2, first part in question 3, first part in question 4, and question 5, there's only one part to it. Sorry, page 244 of book 2. 244 of book 2. I'll be here at 11 o'clock for those who want to talk to me or need to talk to me. There are trigonometric sheets there from yesterday. You should have them. There are 2 trigonometric identities and equations and geometry. I'm going to stop this recording.